Today, I want to talk about the ugly plumbing of doing pipelines. And specifically, when I'm talking about pipelines, I'm talking about lake-based pipelines. Some would call them big data pipelines, but eventually the ones that you run on top of S3 and not the ones that you run within your data warehouse. This is also the reason a little bit before this session started being recorded. We talked about streaming and batch. So I think that we see a lot of requirement for streaming for lake-based pipelines. And maybe a word about me. I'm the CEO and co-founder of Upsolver. I've been basically doing databases for my entire career and data integration. I spent quite a few years in the Israeli intelligence doing data. It was a very large group, and I led data integration, the data integration domain there. A little bit about Upsolver. So Upsolver was actually created as a result of a personal itch. So we were working on a different startup project, and we tried to unblock the data engineering bottleneck we had, specifically around data pipelines. We tried to reduce our dev cycle by 90%. So we definitely needed to build infrastructure to do that. And eventually that internal project turned into a cloud service, turned into a company. And this is how we came to this point. Upsolver itself solves the problem of lake-based data pipelines, but we do it in a very low-code approach. And I want to double click on this part during this presentation. We work very closely with AWS. We also deployed on Azure, but AWS was first, and we are an advanced AWS partner. We are actually the only official partner for AWS service called Athena, which is an SQL engine that runs and queries data lakes or object storage. And Upsolver has been technically validated by AWS, part of the well-architected program. This is part of what you do when you're actually going to sell with AWS. The product has been in the market since January 19. We have thousands of production workloads, over 1,000 users, from terabytes to petabyte scale at a single customer. And we work both with large enterprises and with startups that basically, if you have data, then you're a potential Upsolver user, and that's a pretty large market. And kind of to start things off, and I wanted you to think about that point because this was an inspiration for me. I started my career as a DBA, and when I worked with a database, I wrote a query. The database generated an execution plan. And I didn't need to think about how that query is being executed. I didn't need to construct the execution path. I just wrote my SQL. That's basically the business logic. There's no way around expressing your business logic. And then the database figured out all the rest for me. And that allowed anyone that had SQL knowledge to be able to do analytics, to create their tables and to query their tables. This is kind of the way I grew up. This is how I know to do data analysis. And when we started going into a data lake, suddenly that truth changed completely. So now if I'm thinking about a big data pipelines, I'm taking something that's very similar to a database execution plan, and I need to actually do the entire process myself. So the entire job that was once done by a database optimizer is now my responsibility as the data engineer. I need to figure out the schema from raw files. I need to code my transformation, usually with code, not SQL. So with Scala, with Java and Python on top of Spark. I need to ensure the data is actually consistent because I'm working on S3. That's an eventually consistent file system. I need to construct the execution path. That's the graph that you see here, the DAG that you're seeing in this image. I need to make sure that I create intermediate or staging steps, and I need to clean my data afterwards. So all that part is still my responsibility. And I actually need to manage the file system. So before databases, I would work with a Visual Basic. I would just write code on top of a file system. But now, when databases were invented, I used SQL over tables. This was the way I like to do analytics. And when I work with a data lake, I need to figure out the file format like Parquet. I need to figure out the file sizes, the compression. All of that is part of my journey to create a table that an analyst can query. By the way, saying again, stop if you have any questions, comments, not a huge forum, so I'm happy to take questions during the presentation. Now, what's Upsolver? I'm going to try to place that in the ecosystem. So Upsolver has data sources and it has outputs like pipeline. We connect to streaming sources like Kafka and Kinesis. We connect with pretty much any object storage. S3 is an example. And we connect with databases like MySQL, like Postgre, and bring the data from there using JDBC or CDC. On the other side of the equation, we work very often with Lake query engines. So Athena, Presto, Trino, Starburst, Dremio, Ahana. There are quite a few query engines that run on lakes these days. And we also work with data warehouses and databases as targets, so like Redshift, Snowflake, and Elastic. Upsolver itself has two parts. There is a visual control plane. That's the cloud service that allows you to create your pipelines. And the other part is the actually executing these pipelines. On the physical level, Upsolver runs on the cloud compute, so EC2 spot instances, so basically the cheapest instances possible. And Upsolver stores and manages data within the customer's cloud account. So we create the file system on S3, and we create the matching metadata layer in the catalog, like the Glue catalog or the Hive metastore. We manage all of that, and eventually we get raw data on one side, and we spit out a table on the other side. So that's the process. This is pretty much the integration and how we run. And for this presentation, since there is a technical audience here, I wanted to focus on some of the stuff we did that were harder to implement, how we implemented those things so our customers will be able to work with a data lake, and the inspiration is work in the same interface, work with the same type of system language you know from your database days, but get all the benefits of a data lake. Have the cost advantage of a data lake, the fact that it's open and I can work with any query engine on top of it. And today that's not the situation. And this is what Upsolver is here to change. This is the company's mission. And I think that one of the big, when I tell people the name data lake, they often think about the term that has been used a lot by companies like Gartner, like data swamps. Eventually a data lake is where I store my data, but not necessarily where I actually see value out of that data, and there is a chasm of data engineering for me to get there. So unless you have any questions, I'm going to dive into the first one, about the file system management. Basically, my objective, because I'm coming from the database world, is I want to work with tables. I don't want to manage a raw file system. When I started my job as a DBA, I got a book with Oracle internals. I think that 2/3 of it was how Oracle stores data, how Oracle optimizes the data that's there. Like all of that is not something I expect every company to just implement. And there are quite a few articles. There is one good one from AWS called Top 10 Performance Tips for Amazon Athena. They're describing all the storage best practices that you need to follow to create a table and actually make it performant. And I think that the hardest one to implement was compaction. So compaction is the process of taking a file system with many small files and turning them into larger files. So if I work with many small files, my query engine is not going to perform. And if I work with larger files, it is going to perform. The more streaming I go, the smaller the files that I'm going to have, the harder the problem is going to be. And I want to show you what Upsolver does under the hood when you create a pipeline. And the process is the following. First, I have a stream and I'm using that stream and I'm writing a pipeline and I'm creating my small files as fast as I can so the user can get access to the data as fast as possible. This would be the step number one you see here. The second step I'm doing is I identify that I have a partition with a lot of small files and I want to compact it. So right now, I still need to maintain data consistency. So basically what I'm doing is starting to write the data twice. I'm writing the data once into partition A, the same small file partition, and I'm also writing the data to partition B, which I'm going to create larger files. Part of the work I'm doing is to migrate all the data that's already in the partition to larger files. And part of it is getting all new updates. So both partitions would be in sync. Once I get to a point where both partitions are synced, I'm performing an atomical operation. I'm basically removing one partition from the table using my metadata store. That would be glue catalog or Hive metastore. And then I'm basically using the new partition and connecting it into the table. Once I'm finishing that, I still need to clean the old data. Otherwise, I'm just going to have several copies of all my raw data. And that process is something that needs to work all the time. So we're implementing the concept of continuous compaction. So compaction isn't something that I can run once a day. Otherwise, I'm going to accumulate a full day of small files and all my performance on fresh data is going to suck. I basically want to do it all the time. And usually compaction becomes much more complicated where you're not doing just append only. So for example, if I'm going to get events and these events can go to any historical partition that I have, now I have to basically compact these partitions again and again. This is not a one-off. Some companies have tried to implement it in a one-off. And I think that understanding that continuous compaction is important. It's something that you mature as an organization into once you start to do pipelines over a data lake. So that's the process of compaction. What you're seeing here is 10,000 lines of code. That's how much code we needed to write in order to solve compaction for the data lake. And that feature is being enabled automatically under the hood. The user doesn't need to configure or tune or pull any levers for that to work on any table that you create. So that was the first one. Stop me if you have any questions on that. If not, I'm starting to describe the second challenge, and that's exactly one's consistency, a very basic requirements. I'm writing data. I don't want to lose data, and I don't want to create duplicates. And then when I'm running compaction, I don't want to find out that I deleted some of my data. I think that piece took a year to mature in Upsolver. And the reason we have this problem is that S3 is an eventually consistent file system. So I'm writing a file, I'm not sure that it's actually going to be there. So if my logic is going to be, hey, there's a new file in my bucket, now I'm going to process it and write a file, that's not 100% consistent. I need to kind of create a mechanism around S3, so I'll actually know that I'm keeping that 100% consistency. And as a data engineer, it's not a fun conversation to have with your user. Hey, I lost a little bit of your data, but there is the reason, and it's eventually consistent, and hardly happens. But it's one of the things that even if you lose a little bit, it creates a lot of pain among users. And the way Upsolver did that is that we create a strongly defined file system, which is time-based. So basically, any time period translates into a file, and every file translates into a task. So if I'm looking at a time period, let's say January 1st, first minute of the day, I know that if I had a source file for that minute, I'm supposed to also have a target file. So we have a system overlooking the file system, and every time we see that the file is missing for a certain time period, we just rerun the task. So this system is designed to work distributedly, and pretty much it's a headless architecture. So every time that I see that the file is missing, someone is going to run that task. And because it's a distributed file system, the concept of idempotency is super critical. And the reason is that if two different instances are going to take a file and process it, I don't want them to write two different results. So one of the operations you're not going to see in Upsolver processing is random, because random is not deterministic. It's not something that makes sense in this type of system. So basically, strongly typed file system, idempotent operation, that gives you the ability to create exactly one's consistency. Usually some companies would do that would require to do something like a zookeeper to create a head that will manage everything, but that creates kind of one single point of failure. We implement it a little differently. Definitely one of the harder pieces to make sure that the data is really fully consistent. And I can tell you that with quite a lot of our customers, you go in and you find out that they're losing data, missing data in Kafka, losing data from one S3 to the other. So consistency is definitely kind of the feature you're not expecting. You come in and then you find out what data you've been losing. If there are no questions on this, I'm moving to the third one. This is the same image I showed in the beginning of the presentation. And basically, I don't want people to create orchestration graphs. Orchestration graph is something, well, first of all, I can never give this to an end data consumer. So no analyst or data scientist really want to do this work. And I personally think this is also a waste of the data engineer's time. So the engineers should be focused on what's serving the business. To orchestrate a job basically of multiple steps in order to get from point A to point B is something that the system can implement. And since Upsolver is using stream processing, basically we define our pipeline declaratively. So this is a screenshot from Upsolver. What you see here on the left is a schema on read generated from my source. So for example, this would be the schema representing a specific Kafka topic, so nested JSON data in a Kafka topic. And then what I'm doing is I'm writing SQL, and this is not one-time SQL. This is not a query I run once. This is the definition of a job. So I'm going to calculate my table as the result of a query that runs all the time, runs continuously on my source. The concept of declarative pipelines as opposed to code-based or manual pipelines is critical, because once you don't need to construct the orchestration on your own, you're also not in charge of the orchestration, and you don't need to spend so much time on it. So all the area of orchestration in the Upsolver is completely auto-generated from your transformation. A declarative pipeline has a strongly defined source, that would be the schema on read, have a strongly defined output, that would be the result of this query, and everything is the middle is being calculated by the processing system. So this is applying the same concept of database optimizer, but applying that concept to data pipelines. So this is how you work in Upsolver. Doing this process can take 5 minutes to do. So when we do a demo, we go all the way from Kafka to a query engine like Athena in 5 minutes demo. All we need to do is just write a few transformations. It's not that hard to do. And that can be the equal of a pipeline that took you a month to write. I think that declarative data pipelines is maybe the most easy to understand capabilities, and why pipelines are basically broken today with the way you're doing them on Spark or on Hadoop. So MapReduce, in my specific opinion, is not the right way to process data, because it just takes too long, wasting data engineering time, and it will never be available for the consumers that also want to be part and have access to the raw data.
Ori, I have a question on that. So with this declarative language, I mean, obviously it looks like SQL, but you're not executing that directly against existing SQL engines. You have your own execution optimizer for that behind the hood, right?
Yes.
So there'd be, I assume there's probably particular syntax and functions that are specific to Upsolver's flavor of SQL that you wouldn't see in like Postgres queries.
So to create this SQL, and you are right, we are running it on our own engine, and that the reason is that there is no engine that parses declarative pipelines in SQL. So that's something that we did on our own. Every transformation, so every inline function that you have in Postgres, or in MySQL and SQL Server and Oracle, we basically took all of these 4 languages and tried to add as many of these functions into Upsolver. So I would call it ANSI SQL, but ANSI SQL is kind of a lie. There is no real ANSI SQL. So we basically created some kind of average between the most common databases. There are 4 transformations. Upsolver has a little bit of special syntax. One of it is for streaming. So for example, let's say I have a stream of impression and a stream of clicks, and I want to join them, and there is a time dependency between the time the impression comes and the time the click comes. So I have a syntax in Upsolver that allows me to pronounce that. There are window functions. So that, for example, I want to know how many clicks I got from that user for the last 90 days. And there is special syntax for applying updates and deletes to the lake, which is exactly point number 4. We'll get there in a minute. But basically, if I want to update a table that's based on Parquet, I'm able to do that. And we have syntax called replace on duplicate instead of append on duplicate, which is how you usually work with data lake. Those are the key three that are not exactly like ANSYS SQL.
And for your streaming syntax, how similar or dissimilar is it from like Kafka streaming, Kafka SQL flavor for that?
Pretty similar with one major difference. We implemented on all your historical data. So our windows are not limited to data that you currently keep in Kafka. We are basically piggybacking your buckets, indexing your buckets, so you can write window 90 days on 5 million events per second. It will still work. So that's a big difference. I think the combination, the difference between what you would do with the Kafka stream and Upsolver is if you have just need to process real-time data, you can do that on a Kafka stream. If you want to combine your real-time data with your historical data, that you cannot do, and that's something that Upsolver would solve.
Okay, thank you.
My pleasure. Okay, so challenge number 4, we already started to touch on it. If a data lake is kind of the crippled brother of the database, then people would not want to implement their database on top of the lake. And append only is one of the points that hurt the most. So I need a update use case because I want to replicate operational databases, something like a CDC. So I need insert, update, and delete capabilities. I want to do GDPR. I want to delete user data. I just want to create fast dimension tables and connect them to my dashboard instead of scanning all the events. So there are a lot of use cases for append only, and no company in their right mind would say my data warehouse is built on Parquet if they can't do any updates to the data. So this is something that we heard for maybe 70% of our user base before we added that capability. And the way Upsolver is doing this is we're doing it on vanilla Apache Parquet file. So I'm not sure how many know that, but the standard way, the way data lake table started was with just Apache Parquet file and append only. And then you started to sync specific file formats that add this transaction log or this specific manifest next to the Parquet in the form of Apache Iceberg or Hoodie or Delta Lake. But these were, it kind of turned the file system to be non-compliant with many of the query engines. So we tried to figure out a way to use the same commonly supported Parquet files, but still apply updates and deletes. And we do it in the following way. We are using Hive views or just views, and we basically divide the data into two parts. We have our partitions that are just append also with finalized data, and we have sorry, that will be this part. And on the top, we have kind of a log of changes. So if I'm getting an update, I'm not actually applying the update immediately. I want to still have the ability to do fast ingestion. So I don't want to actually apply the update on the spot. I'm writing the update to my write-ahead partition. And when the user queries the data, they're basically doing a join between my log of changes in my write-ahead partition to the partitions with the data that was already finalized. The way to say data is finalized is basically to compact it. So I'm taking my list of changes, applying it to my historical data, and then I have final data. That's basically the process. But this process would never work without continuous compaction, because the longer my list of updates is going to be, the less performant the join is going to be. So I'm basically joining all my data with a huge list of updates. That would not work, especially on a data lake that's not indexed like a relational database. So the faster the compaction can pick up those updates and implement them, the better the performance that you're going to get. I think that the approach of basically resolving conflicts or updates in query time makes a lot of sense for a lake, because you don't want to slow down ingestion. One of the big advantages of a data lake is that I can basically ingest with the throughput of S3. And once I start doing synchronous updates that need to scan my file system before I finish the update, I can be working 1,000 times slower. So that's why we decided to resolve the conflicts in update time. And we decided that we'll do our best to make the performance work well using that approach, and it works. So by the way, for very high scales. So this is how we implement it. This is also part of the reason that the compaction I talked about in the beginning became very complex, because now we need to work with streaming updates on top of Parquet, and that's very different than updates that we need to do every once in a while. Pausing to see if anyone has any questions.
How do you how do you solve the consistency problem with that?
The view does that. So the view basically joins your list of changes with your compacted partitions. And then when you're doing the join, you're ensuring that the data is going to be consistent. You resolve it in query time. Oracle does that internally for you. Mm. So this is basically taking almost everything that I showed here today is taking the Oracle internal architecture and basically re-implement it in an open way. Very similar to what a database optimizer does. Answers your question?
I'm guessing that's a yes.
Okay.
Yeah.
Awesome. So kind of to summarize the way we look at it, going back from the ground level to 20,000 feet, databases automated ugly plumbing for us. Users could be focused on doing analytics. They have access to the raw data. That would be the raw tables in a database, not exactly the raw files. And in data lakes, data engineers are forced basically to do all the ugly plumbing that the database optimizer was doing for them. The reason Upsolver is here is to change that and basically allow you to implement the database on top of the data lake infrastructure. So the cost of a data lake, the openness of a data lake, but the same interfaces of SQL. We want to make data engineers' life easier. So we see data engineering, especially because there are so few data engineers today compared to the demand. The data engineers shouldn't be wasting their time on ugly plumbing and pipelines. They should enable the organization to be independent as possible, not necessarily develop something that 100,000 companies are also developing, solving the exact same problem again and again for every table. I think it's my opinion, but I think it's also the truth. Upsolver is the only solution in the market right now that allows a person that knows SQL to write the most complex data pipelines on any scale. And this is why the customers that are using Upsolver decided to use this approach, as opposed to writing Spark pipelines or MapReduce pipelines, and those that would be the alternative to what Upsolver is doing today.
Well, and to add to that as well, Ori, real quick, if you are a data scientist and accustomed to Python, we have the availability for Python UDF as well to be able to do functionality and treat the database and pipelines as you would as well. Well, with the added.
True. The SQL is extensible. The SQL is extensible. We can't implement any function in the world. So I always show the example of arctangents. No database in the world has support for arctangents. I can just go to Python, import a math library, and add that into my language. So I never get stuck, and I'm dependent on the vendor to do my transformations.
So that means I can bring back the random function, right?
You can try, but that wouldn't be a good architecture. I think this is one of the things that people don't necessarily get immediately, the idempotency. But think of the database world. For example, I had a database, and now I wanted to replay some data into the database, basically do a big burst of writes into my database. Then I needed to go to operations, talk to some guy and explain everything I did, write a protocol to what I'm going to do, and then wait until 2 o'clock at night so I wouldn't interrupt with the workload of the user. That was one of the least favorite jobs for me. But when you work with an event sourcing architecture, basically you have all your data on S3, and all you're doing is taking data from one S3 location and putting it in another S3 location. You have practically unlimited throughput. You don't need to ask permission from anyone. I can just take my event source and replay it. But there is no value in event source if every time I'm replaying the data, I'm going to get a different result. That's why every time I'm running the process, no matter which instance I'm using and what time I'm running it, I'm supposed to get the exact same result. Cool. So finishing where we started. Hiring. You're welcome to reach out to me. I always answer the emails I get eventually. Upsolver has a community edition. You can try and kind of start to understand what the product does. There are also a bunch of videos online. We run monthly workshops where you're building a data lake on AWS, from Kinesis to tables that you can actually query in SQL. It takes about 90 minutes to run through that workshop end to end. You're welcome to try it.
I also recommend that Joe is a partner of ours and does know Upsolver as well. So if there's questions and you're looking for a friendly face that you know, he's someone that you can reach out to. And from our side, if you have any questions or anything of that sort, I'm actually going to put my contact information, other than either you write Ori directly or you can write me. I'm happy to answer any questions or get the right minds in the room to answer your questions or whatnot.
That's awesome. Thanks, guys. I do have a question, Ori, and it's kind of more of a macro question. Where do you see the space? I mean, there's your classical data warehouse world right now, right? In the cloud data warehouse, with some big players, and then on the other end, there's the data lake and lake house, and it seems to me that they're on a collision course together. What are your thoughts on that? And like, where do you see data lakes, maybe in the next 2-3 years?
Good question. Not an easy one also. I agree, but I agree. And I said it, and I agree with you. So let's look back and see kind of how the cycle, how we're basically in the same cycle. We had Oracle, and I did everything on Oracle. So we did machine learning and text search and a high scale. So all the things that Oracle was not built for. And every time we needed to use a different engine, we needed to do replication. We were very locked to Oracle. We never liked the price. So now, why did we get to that dynamics with Oracle? The reason is that Oracle stored my data in a proprietary format. And it was great for SQL analytics, but it was not great for other things. So looking at what's happening today, Snowflake is basically trying to take the same position in the market, but in the age of the cloud. It's a proprietary data store. They started from being a warehouse, solving BI, and they're trying to basically become your data platform for everything, every possible use case. Some they solve well, some they don't solve well. But that's kind of putting you with you decided and you're kind of locked to one vendor. Then you have the data lake. The data lake evolved from a low cost solution for large workloads. And the data lake was missing a lot of capabilities for it to actually be called a database. So now in the old days, you had Cloudera and Hortonworks and MapR, you did Hadoop. And now in the age of the cloud, you have Databricks, but still it's a data engineering tool. This is the tool for data engineering that writes code. So it's kind of the same problem you had with Hadoop, you still have in the Spark ecosystem because it's the same ecosystem. Now, the collision course makes sense because the data lake wants to grow up to be a database and the data warehouse wants to expand and be a data lake. One option that you see a lot is that you just combine the two. I'm going to have a lake in the beginning as a staging area. And the data warehouse, the target will be just one of my targets. So the master data store is the lake. The BI solution would be Snowflake, for example. And if I want to do machine learning, I'm also going to send the data to Spark, and I want to do text search, I'm going to send it to Elastic, or I can work with multiple solutions. A question that comes to mind, so if I have all my data in the lake, why shouldn't I also query it there? why do I actually have to send it to somewhere else? And this is what I see. I see that the trend of data lake tables with Starburst and Dremio and Athena and Iceberg and Hoodie and Delta, kind of everyone are trying to solve that problem, basically re-implement the warehouse, but implement it as a lake house. And the lake house is supposed to be open as opposed to the warehouse. So right now, Upsolver works with two of these paradigms. So there is only data warehouse. We are not doing this. Lake and warehouse. So we help manage the data in the lake and send the data to the warehouse. And we are also helping with doing your analytics directly in the lake. If you're asking me 5-10 years in the future, what's going to happen, all your data is going to be stored on S3. And the databases are basically going to be more pure query engines and more like APIs to your data. one API is going to be SQL, another is going to be text search. So all of these use cases are basically going to be APIs on top of the data. This is strongly supported by the cloud providers because they want to be the master data store. They want to be, this is kind of the new infrastructure. I had compute and I had storage, but now I have data store. I have data that's actually queryable. It has metadata attached to it. I can go query it. And now I can just pick and choose my best query engine according to my use case and according to my actual specific preference. So I tried to, and I'm giving you a very long answer, I actually tried to test that theory, and I asked a bunch of people, a bunch of heads of data, what will be you using for data analytics in 2 to 3 years? And they kind of give you all the names of all the startups in the ecosystem. But now ask them what are they going to use in 10 years? So you're kind of putting out of their comfort zone. The most common answer by a big gap was S3. So they see their data being stored on S3. The rest is a question mark. So definitely there is a collision course 5-10 years from now. I think the data warehouse is going to be disassembled into multiple components. You could manage your storage, your metadata, and your access control in a central location in the cloud. That's kind of what I believe that's going to happen.
Yeah, that's really interesting. Yeah, I think there's a lot of validity to what you're predicting. So yeah, it'll be interesting for sure. So
I also think
what's that?
Sorry, I also think that there's a shift that's kind of moving more towards data engineering instead of being a bottleneck, but actually being something that's allowing the customers to do what they need to do. Now, I don't want to go down the path of what we had with self-service, where tools were created to do self-service, but as we know, it still required something on the front end. And so a database and data warehousing and data lakes, to me, it's going to be around what is the best way in which you're able to use all of your data and be able to provide access to that data to those that need it where it needs to be. And so tools like Dremio, Starburst, all the distributed querying tools is really about, you've got those that understand how to query, but don't understand the engineering on the front end, but want to be able to access and take out the data that they need and use the data they need. So we're starting to see those tools pop up now.
Mm-hmm. Yeah, I tend to agree. I think the role of data engineer is definitely going to be changing a lot in the next few years, and it already is. It's moving away from being a glorified plumber to, I think in a lot of ways it's going to be a lot more enterprisey as well. We talked earlier before the show about data quality testing and stuff. I think that's one area where you're going to see data engineers focus more on, as well as just playing more of a support role and an enablement role versus as you call it, a bottleneck. So yeah, definitely.
Go ahead, Ori.
There's the whole concept of data mesh. If I'm going to ask you, do you think your QA should be embedded in your team or be a central QA team? Some would say A, some would say B, but you understand the value of having a QA person in your team. The same applies for data engineers. So today it's only centralized teams. That concept of data mesh, and I really like that very long article on data mesh and going beyond the monolithic data lake, is that data engineering is going to be embedded in the team and they need to show business value as opposed to being a glorified plumber. And I think that's that article on data mesh basically said that the third generation of lakes is going to be data engineers embedded in the team with strong self-serve capabilities. And I think I actually went and checked the numbers, and the number of data engineers of the world is 1 in 25 to the people that know SQL. And kind of if I go back to the DBA days, the DBA was an unloved bottleneck for engineers. So now multiply that by 25. And the number of data lakes, paying customers that I saw that, companies like Cloudera has, were in the 10,000 range. So Cloudera, Hortonworks, and NFR, all the Hadoop data lakes. And S3 has, I think, about 2 million customers. So we have 100x growth in number of data lakes, 1 in 25 ratio between people that know SQL and people that can actually do big data engineering. And this is a very large scale problem.
Well, and I think that one thing that's on the surface of what you're talking about, the data engineering is some of this plumbing layer, but the problem that's not being solved that could be exacerbated, right, when you make self-serve tools is 3 different teams define a schema definitions, or you define a metric that uses columns differently, right? That sort of proliferation of not necessarily like how the data is being used, which is not being solved kind of at this layer, but that is that the realm, and maybe, yeah, Joe, I'm interested in your opinion too. Is that the realm of where the data engineer is going to be providing the most value?
I don't know if the most, but definitely tools that allow you to improve your quality of data and allow people to collaborate and understand the lineage of data brings business value. So like, is it plumbing or is it business value? What you said is business value.
Yeah.
Pipelines is plumbing. So I think that you're right. This is going to be something that data engineers need to do well.
Well, I mean, look at the number of data ops companies and data. Well, just look at the number of data companies, period. And Matt Turk's slide that came out a few weeks ago, I mean, that was just like mind-blowing. How many companies? We had a joke. I think there's more data startups now than there are atoms in the known universe. So, Dylan, you can actually correct me if I'm wrong on that one. So,
it's close.
An astrophysics background. So,
Yeah.
but you know, so what I mean, the point is, it's interesting. I think, and it kind of echoes your point, Ori, of you know, you talk to people, data leaders, and it's like, you know, they point to the tools they'll use, but you extend that out past 5 years, and I have no idea who's around at that point. But there will be paradigms, right? What you're seeing right now, again, is the enterprise-ification of all things data, observability, quality, all the stuff that was basically too expensive and too cumbersome for small companies to embrace. It's finally here, and it's just getting started. So,
and there is a good question: what's going to be a category and what's going to be a feature company that's going to be absorbed? So data quality is a question mark. Like data wrangling has always been a question mark. Is it a category, or is it something that eventually I'm expecting to see in another system? And data quality is a more extreme case comparing to data wrangling. So I'm not sure it's going to be a category. It's definitely going to be an important feature. It's something that we need to do, and maybe someone would surprise us and prove that it is a category. I'm definitely all for it.
Well, and I think that the big one that I'm looking at too is sort of the inversion of everything. If all the hype around Web 3.0 is to be believed, that's sort of the dark horse, I think, that could change a lot in terms of even how the cloud operates. If you have a like cloud 3.0 or whatever stupid buzzword you want to come up with, that could be very interesting when you start having decentralized infrastructure. So I would say at the rate everything changes, anything's possible, really. So there's a great company not on that list. Yes, I believe it starts with the U, ends with an R.
Yeah.
They have a mascot, Upsolver. Yeah, exactly. That's what's crazy about this that list that or the infographic that Matt Turk did. It's not complete. It's just even crazier.
The infographic?
Yeah.
Well, it's the same
Should
thing.
link it, Joe.
It's all based on where the investments are coming from and who he's actually paying attention to at the end of the day.
Mm-hmm.
Yeah, it's great. I'm gonna stop recording. Ori, great talk, great conversation. People feel free to hang out and chat more. I just want to cut the video off. So, thanks.